Yeah, all right. Hi, good afternoon. So I'm Zach. This is joint work with Wes, who's at STI Semiconductor and who was at Microsoft Research when we worked on this together. It's also joint work with Earl, who gave a talk yesterday on completely unrelated research. And I'm going to be talking to you about intentional functions. That is not a typo. It is spelled with an S. Today, when I'm saying intentional function, what I mean is a function that, in addition to being callable, has other behavior associated with it. Okay? So there's some precedent for this. Andrew Appel had an extended abstract in 1995 proposing an intentional equality operator that's meant to determine whether or not two continuations are the same continuation, right? Also, you can think of, as another example, projects like Cloud Haskell and Scala Spores as an example of intentional serialization, right? In addition to calling a function, you can serialize it, transmit it to another runtime, and call it over there. So behavior more than just calling the function. I want to generalize this today because I have a particular motivation that drives me nuts, is that I keep finding reasons to calculate deductive closures. And in those deductive closures, I want to deduplicate continuations, right? And oftentimes, I represent continuations as functions. And I would like to ask if two functions are the same or compare them or what have you. So I'm going to be talking about intentional functions, which is a language feature that we added to a proof of concept implementation of GHC in order to address that problem. And because it's GHC, I'm also going to be talking about something that we're calling an intentional monad, which is the natural consequence of re-encoding monads using this type of function. All right, I'll wrap up and take questions at the end. I'm going to start by talking about that motivation of mine, the thing that drives me nuts all the time. Computing deductive closure is probably something that you're generally familiar with. Just to set the stage, I have a set of facts. I have a set of deductive closure rules. I would like to plug into that set of deductive closure rules every fact that I have that fits in all of the places that it fits in order to see whether or not I can reach a conclusion. And once I've reached a conclusion, well, I add it to my set of facts, and then I propagate it through as well. And I keep doing this until I run out of combinations, and then look, closed set of facts, right? One thing about this process is that when I when I close over these things, sometimes I learn the same fact in two different ways. But since I'm after a set, knowledge is idempotent, right? It doesn't matter if I learn something once or 100 times, I still know it. So in terms of my computation, I can deduplicate that. I see I've learned this before. The second time I pick it up, I go, oh, I already know about that, right? I set it aside. I don't bother doing any additional computation because I found that second proof, because that doesn't matter to me in this domain. This is all standard stuff, yeah? It's interesting to observe that you might also wind up having these sorts of duplicate computational trees. Depending on your domain, this happens more or less frequently. We were working on a project where this was very, very dense, right? Where it was not that uncommon to have two partially specialized versions of a closure rule that were, for whatever reason, provably equivalent. And at this point, what I'm saying is that no matter which third fact I plug in for that third premise, both of these things will give me the same answer. So I don't want to compute the whole tree and have to find a bunch of duplicate facts it believes. I want to say, OK, I deduplicate that, right? Save me the work. So I don't just want to deduplicate facts. I also want to deduplicate these computations that I have in progress to save myself the effort of getting the answer to the question, all right? Here's a concrete example of what I'm talking about. Three-premise deductive closure rule with two different forms of fact matching the previous picture. If you're very fast and very much in the know, that is CKY parsing written as a deductive closure rule. And if I wanted to implement this in Haskell, I would start by writing a couple of data types to represent whatever information my fact carried around with it. And then I could write this deductive closure rule as a function that starts by taking the two facts that I would like to satisfy the two premises I started with, right? I satisfy those things because this is a programming language and not like an actual closure engine. I'm implementing all of that. I have to check to make sure those variables match. And if they don't, well, that means that these facts don't actually satisfy the rule, right? They don't actually apply. But if they do, then I'll wait for my third thing, right? Once I get the third thing, then I'll check the meta variables again. If these values match up, then lo and behold, I've learned something. Good for me, right? I presumably have some sort of engine that's pumping this thing with each of the different combinations. And I'm not going to put that up on the slide. But whatever type signature I have associated with this, the engine is taking functions that look like that and just feeding them all of the combinations it can come up with. So once I've got this code, let's think about what it looks like when that engine calls this thing. I might call it with these three arguments, yeah? And when I do substitution and reduction, I wind up with something that looks like that. Yay, I learned a thing. And that first kind of duplication I was talking about of facts can be witnessed when maybe I've got a set of other facts that I know. This in CKY parsing would be like a ambiguous parse, right? If I substitute and reduce, I get the same thing. Look, I've already learned this before, so I don't push this back through the engine, right? I've seen this thing before. It's in my set of knowledge. I don't try to build another tree out of that. I can just ignore it. But this is a degenerate observation of a broader thing, like a degenerate version of a broader observation we can make, which is that if I throw away that third argument, these two sub-expressions, when substituted and reduced, produce the same result, the same function, the same continuation on my computation, right? They're really just that chunk of code with several of the variables replaced with particular values. And so what I want to do is say, hey, are these equal, right? So that if I find out they are, I can throw one away and not have to do that whole subtree of work. Of course, the catch is this is a function. And I'm not allowed to ask that question because blah, 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 theory of computation. Yeah? Like, it's a problem because if I can actually answer that question precisely, then I've broken a lot of things. So the reason that I'm talking about all of this is because I found this to be very frustrating. I can respect that asking if two functions are equal is not a problem I can solve in this language, but I also get really irritated because I know what's in the language runtime, right? This isn't what's in the language runtime. A closure is what's in the language runtime. And in this case, that closure, a pointer and all of the values of the variables that have been captured, those are equal. And so I should be able to argue to myself, these are going to do the same thing. But the abstractions of the language prevent me from being able to do that. So the summary of my problem is that I have these continuations encoded as functions. And I want to be able to deduplicate the continuations. So that means I'm going to need to ask whether or not those continuations, those functions, are equal. And worse than that, I need to be able to ask how they compare and how they hash, right? Because I need to be able to put them in a data structure and then ask if they're there, right? If there's an equivalent value in that. Fortunately, when you actually write code that looks like this, you don't write the same thing in several different places. I don't actually need to know if two functions are equal. Because if they are, it's almost certainly because they came from the same place in my program, right? And so in this case, I don't need to know whether they're equal. I need to approximate conservatively whether they're equal on the basis of that runtime representation, the closure that I know is already in the language runtime. Okay? And I don't want to just solve equality and sorting and hashing, because this is my frustration, but you might have your own. Right? Somebody else might have their pet project where they go, well, I want to know the following thing about this closure. And so we should be able to generalize this idea. Now, before I talk about how we do that, I do want to mention defunctionalization is a way you'd solve this, right? Instead of representing your continuation as a function, maybe represent it as a first-order data structure. And then you can write whatever code around that data structure you feel like. I've done this a lot. I've gotten really tired of doing this because it's very effective, but it's also really clunky, right? The code you wind up with at the end is harder to read. It's easy to make a mistake when you manually defunctionalize. I don't want to have to do that. I want the system to do some of this work for me. And so the way I'm going to make that happen is by writing functions that look like this. This is an intentional function in our Haskell extension. Again, proof of concept. I don't want to oversell that. This is an intentional version of the standard library function const, which takes two arguments and then returns the value of the first one. And when I say this is intentional, what I mean is it's got this position here for a constraint function. A constraint function is a thing that makes an assertion about a type. In the case of eq, it's saying, give me a type, and I will assert that that type has a definition of a quality associated with it. So when I attach this constraint function to that intentional function, what I'm saying is that every value captured in the closure of that intentional function has to conform to it. This x, which is free in that sub-expression, has to be of a type that is equable. And you can see that I've got up here on the type signature that assertion. So that way you can't call this with something that isn't itself associated with the definition of equality, right? So once I do that, the type checker will let me have this conforming type b arrow %eq a, an intentional function from b onto a, where everything captured in closure is eq. What can I do with that? We have three destructors. The first one is application, because it wouldn't be much of a function if you couldn't call it, right? But I've got two more for you. One of them is identify, which asks for an ID associated with the function. The function's ID is going to be its definition site. Think like just the program point where you wrote the function. And the second part is going to be inspect. This is the other chunk of your closure, right? This is going to be the environment of values captured by the closure over this function. Here, you'll notice it's not just the values. I have this existential because I know that everything in this closure conforms to the constraint function. So it's the values together with a proof that every one of the values is, in this example, equatable, right? Once I have these things, I can start writing code for the functions themselves. So if I have a function from a on to b which is equable, right, which has that constraint function eq associated with it, then I can say these two instances of that type are the same if they are defined at the same place and they have all of the same values captured in the environment, right? The closure captures the same environment of values. And again, this is a conservative approximation. Two functions could be equal, and this would still say false, because they do the same thing, but they're defined in different places. I just don't need that, right? And the nice thing about the constraint function being a parameter is pick whichever one you like, right? Here's a definition of sorting these things, so you can put them like a tree set or something. So what I'm saying is we're using this runtime definition of what a function looks like in order to make that definition transparent to the programmer. In this language, we're representing partially applied functions as these closures. And so I'm just making those closures transparent, making them accessible to the programmer so they can use that information to define whatever kind of behavior they need. OK? We have a formalization of this as a little lambda calculus. Lambda ITS includes intentional functions and a whole bunch of other stuff because we wanted to make the case that they were actually useful for something. It does not include extensional functions because we didn't need them, right? So that means that every function associated, like in this lambda calculus, is associated with both an ID and its environment explicitly, as well as the body expression, which is still undergoing traditional substitution. OK? We have a proof of soundness. It works by encoding down to an extensional language with GADTs that is itself sound, right? So the soundness comes out of an encoding. But more interesting to me is this property we were calling closure consistency, which is that if you have two of these functions that have IDs and environments that match, their body expressions will also match. They will be syntactically identical. And this is the basis on which we can argue the correctness of that conservative approximation. OK? One other quick point, eta equivalence doesn't hold anymore, which I guess isn't that surprising, right? Because I just added more destructors for functions, so you could probably tell things apart a little bit more easily. In particular, when you eta convert, you introduce a new program, like a new lambda definition site. It's going to be a different ID. And so these don't look equal to that conservative approximation. If you restrict to just application, of course, you still have eta equivalence. But we're not restricted there. We have these two additional destructors that allows us to tell these two functions apart. OK? We have this implementation. It's based on GHC 9.2 because it took us a while to get it together, and that was what was fresh at the time. It works by encoding to GADTs the same way the proof of soundness does, so it is not fast. If we wanted to actually make this thing like industry ready, it would take a lot more like deep exploration of the compiler because we'd have to integrate these destructors with the actual runtime representation. Right now, we're doing this wrapper encoding thing. But using this proof of concept implementation, we can take that code that I had up here before. And remember how I was saying I just want to be able to take that function and put it in a set or something and see if I've seen it before? I can just slap %ord on all this. And lo and behold, as long as everything captured in the closure of all of these functions is comparable, now I can ask whether or not these two things like are equal, how they compare to each other. I can put them in like a tree set. I'm good to go. One last point I want to make about all of this. That's not the code you'd write if you were actually writing a deductive closure in Haskell. Like taking a step back from intentional functions for just a second, if I were writing a deductive closure in Haskell, I'd write it as a monad, right? Like I have some do syntax. I like this code better because if you're familiar with do syntax, this is faster to write. It's certainly faster for me to read. I think I can pick the deductive closure rule I had up previously straight out of this code. I mean, I probably wouldn't write it with guards, right? The guards are like a linear search. And so I'd probably have some sort of indexing functions. This is what I'd prefer to write, though, as a Haskell programmer, right? Speaking just for myself. The thing is, if you desugar this, you can see that that function right there is the one that I want to deduplicate. And it's still a function. So if I just go through here and turn these all intentional, Suddenly, I don't have this problem anymore. The thing I need to deduplicate has a %ord associated with it. I can ask if I've seen it before. I can check it whether or not it's in a set. I can put it in a set, etc. And of course, I don't want to look at this, so we're going to hide it behind our own form of do sugar. But the general idea is that now we have this intentional monadic environment in which you can write computations that conform to constraint functions. Computations that, in addition to being evaluated, can be subjected to operations like compare or hash. Okay? So the broad theme of the work is just that the compiler already knows everything I've just said. Right? The compiler has this information. I just want it to share with me. So that way I can do things efficiently, assuming that the compiler were actually not just a proof of concept. But I can work with the information the compiler already has and not have to do things like manually defunctionalize. Right? Summary. Intentional functions are functions that have operations other than just application. I've been talking about these. You could have your own. Intentional monads are computational environments in which you can write computations that have these properties. Lambda ITS is our formal lambda calculus that gives us a way of arguing the correctness of conservative approximation that I've just been talking about. We have this proof of concept implementation. You can play with it on GitHub if you'd like. Questions, please?
Hello.
Hello.
Very nice talk, thanks. So you're using GADTs in the implementation, so you mean that you're actually defunctionalizing the code?
Yeah, the implementation is basically just doing automated defunctionalization right now. But the observation is that that's just what we did so we could make sure the language feature worked the way we thought it should. You wouldn't actually do that if you wanted to make the compiler go quick.
So you're saying this is slower, but what's the reason it's slower than?
We haven't gotten to break it apart in too much detail, but the conversations that we've had and the tests that we've run point basically to the fact that by using this GADT encoding, we're preventing the compiler from inlining a bunch of things. The GADT encoding is capturing each element of the closure as a single value together with a pointer to the implementation of a thing, like eq or whatever, which prevents it from inlining.
And also, so it's less flexible than it could be, right? Because you have to have a closed world assumption. You have to know all the sites where this function
we
could be
need
created.
to be able to produce unique IDs for all of the intentional functions that are running. But those unique IDs are actually generated from the hashes that the Haskell module itself uses to uniquely identify compiled modules. And so strictly speaking, the way that we're getting around that is by doing that thing where you pretend that hashes will never collide, the same way that the compiler that we're already extending does.
OK.
Yeah.
Cool. Thanks.
Thank you.
Clarification question. Can I bring my own type class to make a constraint?
Absolutely, you can. OK.
Are there any, and there are no lowercase c constraints, I guess, on what that involves?
The one limitation I can tell you is that you cannot then write an implementation of our ID data type for your type class unless you have some way of getting your hands on the contents of it. So as long as you can write the definition of your type class for intentional functions using eq and ord and hash and whatever else we provide for the ID type, yeah, you're good to go.
OK. And then if I'm not very imaginative and don't know what other kinds of operations I might want to perform on my intentional functions, other than the ones you demonstrated, what are some common ones that you could think of?
I mean, so far, the only things we've really looked at are the ones I named, eq, ord, hash, and also serialization. Although what does stand out to me is that basically everything else I can come up with requires at least some level of system support for an implementation of that thing. So deserialization requires some kind of runtime support.
OK. Thanks again, Zachary.